Okay, I'm recording now, and let's start 5.6. 5.6 and 5.7 are basically the same idea, just split into two sections. We should know from grade 9 what a linear relation is, but let's define it kind of using technical terms here. A linear relation is when you have a constant change in the independent, which of course means the x variable, results in a constant change in the dependence, which is the y variable. Now, what do I mean by the word constant? In other words, isn't changing. The change isn't changing. That sounds bizarre, but it's really easy on a graph to tell the difference, especially between a constant change and not a constant change. Okay. A linear relation always makes an equation that you already know. We've been playing with this. You saw this in grade 9, and we've spent some time this unit that's really going to pay off now, reviewing old grade 9 stuff. This should be real familiar to you. The equation for a linear relation is always y equals mx plus b, where this y is, of course, my dependent variable. The x is my independent variable. And we know what m and b mean. And again, my nicknames for them are move and bump. What do I mean by bump? What am I bumping into? The y-axis. This is called the y-intercept. Got to use that fancy word. It's where my line intercepts the y-axis. Or again, it's where it bumps into it. B for bump. And m for move. What do I mean by move? I mean the rate of change, which is a constant rise over run. Okay? There we go. I love the way we're bringing the grade 9 stuff together here with the grade 10 stuff. Example 1, determine if the given table of values represents a linear relation. It's not that easy to tell by looking at the chart. Looking at a graph, and I just graphed these a minute ago. You saw me entering the data. Where are we, data? Data, there we go. Okay, so let's see. Let me ungraph that one. That's the first one. Okay, let's see. Let's put, where can I see all the dots? There we go. Can you see that? Clearly not a straight line, right? Very definitely not a straight line. So the change in, the change in rate as I'm going from dot to dot is increasing. The slope increases between every dot. The slope is increasing as I move left to right. It's not staying the same rise over run. Now, excuse me, how can you tell that without graphing it? What's the secret here? The secret is to go to the chart and ask yourself, say self, are x and y changing at the same rate? When I go from point to point in the x values, which are in this case t, but whatever, independent variable, I seem to be going up by 20 every time. Definitely that's constant. But it's not really linear unless the other side is constant as well. And the difference from 1 to 2 is to go up by 1. The distance from 2 to 4 is to go up by 2. The distance from 4 to 8 goes up by 4. And from 8 to 16 goes up by 8, and from 16 to 32 goes up by 16. Therefore, not linear. Why? Because rise divided by run is not a constant number. And what does that mean for the graph if you're not linear? You're a curve. Now, does that mean there's no equation for it? Oh, no, that's not true. In fact, there is an equation for this. And this is now my 4th year here, about the 5th or 6th time I've had this course, because I've had a couple semesters where I had more than one section of grade 10. And I've been using the same notes, and I think I can count on one hand the number of people who've gotten this question right. So I'll give you a minute. Anybody want to try to figure out what the equation of this is? You know it's not a straight line. You know it's a curve. I'll give you a minute. What do you do to n? Sorry, let me say that the right way. What do you do to t to get n? So n is some sort of function. Ooh, let's write it in function notation. N is some sort of function of t. There's a rule I can do with the number t that will give me the number n. See if you can figure it out. I'll give you a minute. And then I'll give you a hint and I'll give you another minute. Would it help if you looked at the graph? Maybe, for some people. I can put the graph back if you like. Any ideas? You lost? Well, okay, what do you know it's not? You know that it's not linear, which means what? What kinds of things do you see in equations that curves have that linears don't have? Exponents. That was going to be the hint I gave you after a minute. Did you hear that, guys? Exponents. There's an exponent involved. Now, there might be some people going, well, maybe it's an x squared, or in this case, take t and square it. No. Good guess, but you know what square roots do? They actually curve, can you see me drawing here? They curve this way. There's going to be a 2 involved. Good thinking. What made you realize there's a 2 involved? What do you notice about all of these n numbers? They're doubling. They're from the 2's times table. Does it have all of the 2's times table? No, I don't see a 6. I don't see a 10. So it isn't strictly about multiplying. That gets back to your hint. There must have something to do with exponents. I'll give you one more minute, then I'll just... Once you see it, it'll be like, oh, okay, that's kind of obvious. 2 is involved. Exponents are involved. I'll give you another minute and see if anybody gets it. Last year, somebody did get it. So start looking at the numbers. I do something to this number. 0 is kind of hard to work with. I do something to this number. It involves the number 2. It involves an exponent. And then out comes that number. I do something to this number. It involves an exponent. It involves a 2. And I get this number. Would it help if I gave you one more hint? Okay, here's my hint. The 2 is not the exponent. The 2 is the base. You knew that already? Okay. Then you must be close. Because look at this. Do you guys realize that what is this number? This is 2 to the 0. What is this number? 2 to the 1. What is this number? We're right there.
2 to the power of n.
Very close, except that n is the answer. T is the number I got to work with. 2 to the power of... Very good. T divided by 20. Sometimes exponents can be the variable. We call that an exponential function, and they happen all the time. In fact, population curves tend to be all about having the exponent as the variable. And just to prove to you that does work, if we go back to this graph and we actually graph, let's see, what are we going to graph here? I guess I need the keyboard up. I got y equals 2 to the power of, and then I better open a bracket so that it knows that both of these things are the exponent. And then it's going to be x divided by 20. And, oh, that didn't work. What did I do wrong? Oh, because I hit subtract instead of divide. Well, divided by, that's better, 20. And there we go. Look at that. Hits every dot perfect. That's the equation. Not a fair question for me to ask you because, to be honest, you don't really study these kinds of equations and how to work with them a lot until grade 12. They come up in grade 11 a little, but in grade 12, they're huge. And, you know, all of the talk we've had during this pandemic about flattening the curve, you know what kind of curve they're talking about, is an exponential growth curve. So it's about trying to keep that curve from shooting up so fast that we overwhelm the healthcare system, right? And there's so many people, you end up like poor Italy was in their first wave where, you know, they at first they said if you're over 80, don't even come to the hospital, we can't help you. And then I think in some parts of Italy, it even went down to if you're over 60, you're on your own. We won't admit you. No, I mean, it's not something to laugh about. It's terrible. Could you imagine that happening here? But if we didn't keep the curve from going sharply up, that totally would have happened. And who knows? We'll see how the variants go. But anyway, there it is. That is definitely not linear. What about this guy? This one definitely is linear. Let me prove it to you. I go up by 60, and I go up by 3. I go up by 60, and I go up by 3. See the nice pattern here? For every 60 I go up 3. So it is linear, right? Because constant change in the A value leads to a constant change in the T value. And you know what would be really cool about this? Let's say, okay, don't do this. Stop, don't write what I'm about to write. But let's say that I only gave you part of this data. Like, let's say, okay, this part is also going up by 3 and up by 60. What if I spilled some ink on my data? Oh no, I can't read those numbers. How do I know it's constant now? I can't read any of that. Help me. Well, notice that the jump from 60 to 240, how much is it from 60 to 240? That's 180. And the jump from 3 to 12, that's 9. Notice that that's still the same. You know what? I just wrote that upside down. We want rise over run. This is the rise side on the y side, sorry. So let me say that again. The jump from 3 to 12 is a jump of 9. The jump from 60 to 140 is a jump of 180. Notice that's the same as the jump between these 2 points. 12 to 15 is a jump of 3. 240 to 360 is a jump of 30. Sorry, I wrote 60. I don't know why I didn't say it. I know. Sorry. Notice those are the same 2 numbers. I have some people looking at me with blank stares. Can you see that those are the same 2 numbers? The rise over run's the same no matter what points you look at. The rise over run will always be equal to 1/20th. So that's my equation. Okay, let me get rid of all these scribbles. I messed up my data here. There we go. There we go. So I take the A number, I divide it by 20, and I get the T number. So T is A divided by 120. And this might be where somebody goes, well, wait a minute. Mr. K, you said that all linear look like this. And I'd say to you, yes, it does look like that. You just have to kind of change your perception a little. My y is t. Again, it doesn't matter what letters you use. My dependent variable is t. My slope. It's like, but you don't even have a times by a number. You have a divide by a number. All multiplies are divides if you think of dividing, or if you think of dividing as multiplying by a reciprocal. Instead of saying divide a by 20, isn't it the same as multiplying a by 1/20th, which was my slope number? So there's there's my y, there's my m, this is my dependent variable, so there's my x. Oh, and in this case, what's the b?
0.
And that's very, very useful because in this chart, if you paid $0, you should pay 0 taxes. Government's pretty bad, but they can't tax you on nothing. So logically, that should make sense. So once again, if I go to Desmos, where I put this data in, and okay, let me turn off this graph now, and turn on this one. And oh yeah, it means I got to turn that line off too. There we go. And okay, this one I'm going to have to zoom out some more. Now you can see this is definitely linear. Although it's like, well, I don't know, they're pretty flat. Are you sure that's not a curve? That we just can't maybe see all of the curve? Well, let's type it in and see. What did I think it is? I think it's t, in this case I'm using the letter y. Y equals a divided by 20. So x divided by 20. And yep, it goes right through 0, 0, the way it should. Cool. Now, if I was really drawing this graph, I wouldn't draw it the way Desmos does. I think I'd stop right here. Right? Negative dollars and negative taxes don't make any sense in this context. But you get the idea. It is very definitely a straight linear line. Okay, so that's kind of almost really all there is to 5.6. Notice it was only one page, right? There's a couple of examples on the next page. Oh, there's one more thing we got to mention too. Oh yeah, right. We do have to talk about rate of change. Well, rate of change, we already kind of talked about this, is the same thing as saying slope. Here, I'm actually going to just put an equal sign. Rate of change is what we call slope in a linear equation. And in this case, it is the change in y over change in x. And again, if we use variables that aren't y and x, big deal. You still know that means dependent and independent variables. And we actually do have a symbol that we use in math that always means change. We use, it looks like I'm drawing a triangle, but this actually is a Greek letter. It's the Greek letter delta. Delta y over delta x. And we can actually put this into a formula too if we like. If I had 2 points on my graph, I could say that the change in y is the second y coordinate minus the first y coordinate divided by the second x coordinate minus the first x coordinate. Assuming that I have 2 points, and I call those 2 points x1, y1, and x2, y2. We will formally look at this formula a lot more closely in the next chapter, but it's handy to kind of remember right now. For example, let me just make one up here. Suppose I had the data x over y is 1, 2, 3, 7. There, that's not going up by a constant amount, is it? I go up by 1, I go up by 1, I go up by 4. And then the responding data is I plug in a 1 and out comes a 1. I plug in a 2 and out comes a 4. I plug in a 3 and out comes a 7. I plug in a 7 and out comes a 19. That's hard to tell just looking at it if it's linear or not. And in fact, it is linear. Because when I go up by 1 here, I go up by 3 there. When I go up by 1 here, I go up by 3 there. Okay, so far so good. 2 of these, of course, any 2 points could be in a line. You need a third point to know for sure it's a straight line. And this isn't going up by the same amount. Plus 4, plus 12. But isn't 3, remember, rise over run? Isn't 3 divided by 1 the same thing as 12 divided by 4? So therefore, yes, it is linear. Or again, to go from one point to the other, if I call these 2 points here, if I call this x1 and y1, and I call this x2 and y2, I can use this cool little formula. My slope is y2 minus y1, so 4 minus 1 over 2 minus 1. You can think that way too. If you like that, the way they talked about, those of you at home probably couldn't hear that. Somebody mentioned final minus initial. If you like thinking about it that way from your physics class, sure, that works. In math, we usually like to use little 2's and 1's, but final minus initial means the same thing. And notice this gives you 3. And if I take these 2 points here and call this one my x1 and my y1, and my x2 and my y2, the slope is 19 minus 7 over 7 minus 3, which gives me 12 over 4, which gives me 3. The slope is 3. So I'm going to write that in words. Between any 2 points on this piece of data, the delta y over delta x, the change in how much it goes up and down divided by the change how much it goes left and right, is always 3. So I actually know that this would be y equals 3x. Oh, but I don't know the y-intercept. Uh-oh. How could I find it? I can count backwards. Y-intercept happens when x is 0. If I count 1 this way, I go 3 that way. So if I counted 1 backwards, I should go 3 backwards from 1. Where would you end up if you counted back 3 and you started at 1? Just to check, any one of these points should make that equation work. Let's try one. Let's try 7, 19. 3 times 7 is 21. 21 minus 2, 19. 3 and 7 should work. 3 times 3 is 9 minus 2 is 7. They work. Question? Can I explain? Well, why don't? Okay, tell you what. I'm going to keep going. I got to get through the rest of these notes. When we get to the end of the video, or when we get to the end of the lesson, I'll back up and see if I can re-explain that in a more palatable form for you. Okay, I want to move on to kind of a more real-world example here. A hot tub contains 1,600 liters of water. Graph A represents the hot tub being filled at a constant rate, and graph B represents the hot tub being emptied at a constant rate. What are my independent and dependent variables? Well, my independents, the fact that they put it along here tells me, is time. Independent. Oh my word, I just misspelled that word badly. Independent is time. And my dependent is volume. So let's determine the rate of change of this relationship. So you know what? It's not always easy to read points between here, but notice they give me dots. If they give me dots, I can assume those dots are on the grid lines. So I'm not estimating where they are. So let's see. Change in y over change in x. So how much does x change? How much does y change from this point to, say, this point? It goes from 1,600 down to 800, or actually it goes from 800 up to 1,600. And then how much does it change in the x direction? Well, it was 80 in the second point here, and it's 40 for the first point. So that would be 800 divided by 40, which is 20. Now 20 watts. This has a unit. Liters per minute. How many times in the sciences have you seen a unit that's actually 2 other units divided by each other? That's because it's a rate, and that's because it's really the slope of a linear relationship, like kilometers per hour, meters per second. Okay, graph B, let's try this one. Delta y over delta x. Now careful here. I have to count from left to right. I read from left to right, math's no different. So if this is my second point and this is my first point, my height change is 800 minus 1,600, which is going to give me what kind of a number? Negative. It's going to give me a negative. And you learned in grade 9 that when lines are going downward, the slope should be negative. Notice x is still positive. I'm still starting at 0, and I'm going to 20. So this would be 20 minus 0. And again, if you want to draw this on the page, this here is x1, y1. This here is x2, comma, y2. My first and second coordinates, which is negative 800 divided by 20, which is negative 40 liters per minute. Compare these two numbers. One's positive, one's negative. The positive number has a slope going up as I go left to right. The negative slope goes down as I go left to right. Compare the magnitudes of the numbers. This is a smaller number than this one is. How does that get reflected in the graph? The bigger number is steeper, isn't it? Because it's the same scale on both graphs. Look at the scale. So this is a steeper number, therefore it's a bigger slope number. Okay? All right. Told you 5.6 was quick. 5.7. Oh, hang on. I think I have to go to my other page. There we go. 5.7. Come on. There we go. All right. Intercepts. Do you not have this one? Oh, yeah, of course. Okay, intercepts. Horizontal intercept, also known as the x-intercept, is where a graph crosses the x-axis. And remember, the x-axis is the horizontal line. That's why it's called the horizontal intercept. And if you're looking at data points, it is the x coordinate when the y coordinate is, finish my sentence. Right, because remember, everywhere along the x-axis, y is 0. Does that make logical sense? So you could probably do the other definition yourself. It's basically the opposite. The vertical intercept is what we would call the y-intercept. And it is where a graph crosses the y-axis. Now, I'm actually not terribly happy with these definitions. I'm copying it from the notes that, kind of come from the curriculum guide and everything. But I don't like the word crosses because, linear ones will cross, but curves have x and y intercepts too, and they don't actually have to cross. You can just touch the x-axis with a curve and the y-axis. But oh well, I guess this is the linear chapter, so linear ones definitely cross. And I should probably write the opposite of the second sentence too, right? It is the y coordinate when the x coordinate is 0. All right, let's do some examples of finding intercepts. This will go pretty fast. This is not very difficult, actually. Quick, example 1. What is the horizontal? Are you okay if I start doing abbreviations to save some writing? Horizontal intercept, what is it? 2. It's 2. Somebody usually asks me at this point, shouldn't I write 2, 0? No. The intercept itself is just the horizontal value, not the vertical one. And by same logic, the vertical intercept is just the vertical value. So where does it hit the y-axis? 5. Get ahead of me, try the next two yourself. And feel free to abbreviate further. HI and VI sounds pretty good. Horizontal intercept, vertical intercept. The B one is kind of messing with you though. All right, let's see if I can catch up to you. The horizontal intercept for the first one here in A is definitely 20. The vertical intercept is definitely 100. Can you see those 2 points? Just read them off the graph. Now in B, well, I have a vertical intercept at 100 right there. What would you say about the horizontal intercept? Hey, that's a good, so now that's a good argument here. Should I continue counting this way until I get to the point I want? Yeah. There's very, very few applications in all of science where you can actually consider time as being something that can travel backwards. Particle physics is one of them. But unless you tell me this is a particle physics question, I think I'm just going to say none. We don't have a horizontal intercept. Boy, you know what? If there had been an arrow on here, I'd have totally done what you just said. I'd have counted backwards. But I don't see one. As far as I'm concerned, the domain, ooh, fancy word from last lesson, the domain of my function here is from 0 to, well, 35. I don't even see an arrow on the other side. I don't really know that it goes forever the other way either. Okay? The horizontal and vertical intercepts of a graph have meaning. We need to be able to describe what they represent in the context of a graph. Ooh, I like this part. So first of all, determine the horizontal and vertical intercepts. Okay, let's do that. So vertical intercept is 10. 10 what? 10 centimeters. And my horizontal intercept is 45 minutes. What do these points represent? And every time we ask this question on a graph, there's always some wise guy who wasn't paying attention to this lesson who writes down something brilliant like, it represents where it hits the point on the line. That is not at all what we mean by that question. What does it represent in the real world? What physically are we trying to represent with this line and this dot? We have a thought from the room here. What do you think? Okay, well, you're on the right track. But what does this 10 represent in the real world? How about it's the height, I just misspelled height, the height of the candle, finish my sentence. Oh, at 45 minutes, I disagree with that. At the beginning, at 0 minutes. So how about before we start burning it? One of those like decorative ones or whatever, you know, smells nice, one of those deals. 45 minutes. Yeah, 45 minutes. Horizontal intercept, 45 minutes. And what is this? There you go. This is how long until the candle is gone. And you're left with just a pool of goo. Whatever. What is the domain and range? Well, I would say, I'm going to use fancy words, fancy symbols, I should say. X is greater than or equal to 0, less than or equal to, it obviously has to stop at 0. What are you going to have, a negative height for a candle? Or negative time? No. So obviously these things have to start and end at 0, so I might as well do the range the same way, 0, y. And notice your intercepts are the numbers you're looking for. 10 and 45. And I didn't specify what kind of numbers they are, so what do I assume they are? Nope. Reals. It wouldn't be just integers. Are you telling me the candle could never be 10.5 centimeters tall? Of course it can. At some point in this data, it was 10.5 centimeters tall, right? Somewhere on this height, it was pi centimeters tall. So even irrational numbers are in there somewhere. It's all real numbers. If you don't say, you assume real. Look back in the last lesson, we wrote that down, didn't we? At least we should have. Okay, let's try another one. This graph shows the total cost for a house call by an electrician for up to 6 hours of work. Explain the meaning of any intercepts. Okay, well let's do them one at a time. So my horizontal intercept doesn't exist. What does that mean?
It will never cost you $0.
That is exactly right. You're one of the first people that ever got that fast. Nicely done.
I can learn to understand you much better.
That's scary. Okay. Thanks for your contribution there, Siri, or whoever you are. I'm going to write this way. Under no Scenario, are you cool with that word? Under no conditions, under no circumstance, under no scenario, is it free to hire this electrician? His bill will never be zero. And I just misspelled electrician. It's like what my dad did for a living. You'd think I'd know how to do this word. There we go. Under no scenario is it free to hire this electrician. My vertical intercept is, let's see, what's half of 120? 60 bucks? Which means what? What does that number tell us? Right on. Oh, I like the way you said that. It costs $60 just to hire this electrician, right? Just to get this person to come through the door before they even do any work. Sometimes we call this in the business world. I wasn't going to be, I mean, what? The guy doesn't, the guy shows up, it's something stupid that the person could have fixed themselves, like switching on a breaker. He had to, he had other appointments he could have booked there and made more money. He had to pay his gas to get there. The guy can make a living here. There's nothing wrong with this. I don't think you can call it a scam. You know what you do call it? You call it the flat rate. Right? There's the flat rate of getting him there for 60 bucks, and then whatever happens after that, it's like, well, this job's going to take me 1 hour, then you pay according to this line. Or it's going to take me 4 hours or 6 hours, or I'll have to come back tomorrow, or whatever. Pretty much all service industry things have something like a flat rate. It's the only way to protect them from, several jobs in a row that are way too easy, and then they booked appointment times for them, and then what? They're going to starve because they didn't make enough money that day? No, you got to make a living. What is the rate of change? Well, okay, let's do the slope again. What's halfway between 120 and 240? 180? Am I right about that? Okay, so this is 180. So delta y is 180. And delta x, oh, wait a minute, 180 minus what? 180 minus 60? I'm using this dot and this dot. I'd get the same number if I use the other two dots, or the other two, or the first dot and the last dot, but it doesn't matter. I'll use this one and this one. If somebody wants to use other ones, go ahead. 180 minus 60, that's the height difference. Okay, what's the horizontal difference? This is 3 minus 0. Okay, so 180 minus 60 is 120. 3 minus 0 is 3. And I am looking at 40. What does that mean? 40 what? $40 per hour is exactly right. So that would mean, of course, that's how much it costs to hire him. Feel free, again, if you use any of the other two dots, if you use this one, right, you'd get, what would this one be? 300 divided by 5, which is still 40. Or no, 300 minus 60 divided by 6. That's better. You get 240 divided by 6, which is still 40. The electrician estimates he can complete the job in 2 hours. How much do you expect to pay? Well, let's make an equation. Oh, you just wanted to read the graph? Fine, I want to make an equation. So what is the m? Well, that's my rate of change. And what's my b? Oh yeah, that's the y-intercept. Look at how easy it is to find those things now. And we want to know how, okay, let's maybe change the variables to cost and time. And there we go. Now we can plug in the number. What is the cost for a 2-hour job? Ooh, look at that. I even switched to function notation. 40 times 2 plus 60. And is this the same number you read off the graph? Let's see. At 2, I don't know. Can you tell just by looking at it that's 140? Nah, I kind of trust my algebra more than my eyeballs when I don't have a clean grid to look at. The electrician charges you 180. What does that mean in terms of how long it should have taken? My dad passed away in 2015, and his best friend passed away in 2018. And my mom and I were the executors in charge of both estates. My dad's best friend had like no family. So we had to use kind of the same, so we used the same lawyer we always use. And boy, when I'm looking over, so because settling an estate can take a long time, years, they basically just rolled the two jobs together. And after working with these lawyers for 3 years, we got one bill. You think things like $40 an hour is a lot? You have no, anybody here, their parents are lawyers? Man, the work rate for lawyers is unbelievable. Now, it's different depending on what they do. So they itemize, like when they're doing this part of their work for you, they charge this much an hour, and that part of their work, they do that much an hour. If there's any actual court costs involved, you're looking at $400 or $500 an hour. Yeah, that's if they have to go to court. Luckily, nothing we did ever had to go to court, but that was right there on the bill. They put a 0 by court costs, but the rate, we could see it on the invoice. If we'd have had to go to court, if any of my dad's best friend's distant relatives had decided to contest the will and it would have ended up in court, the guy had not a whole lot to fight over anyway, but you get the idea. If we'd have had to go to court, we'd have been paying this lawyer $400 and something an hour. It's like, ah! Anyway, moving along. Okay, we got to solve that. That's algebra, right? I minus 60 from both sides. I divide both sides by 40, and t is equal to 3 hours. And that's it. All right, I'm going to shut off the video.